Welcome back. We did sound, light, waves last week. And this week I really want to focus on electric energy, and magnetic energy. So it's one chapter for the week. And it may have a lot more in common for some of the things you guys are saying you're involved in with your apprenticeship. So I wanted to make sure we treat that well. And you may know some of these aspects very well. So it should be a little more familiar for you. One of the things I want to talk about, last week we finished off with the light forces and waves, and they're dealing, especially with light, is a wave in the electric force. We also talked about forces in our previous chapter causing a mass to accelerate. And so there are four places that we get force from. One of those is going to be gravity. Letting something drop, then it's going to accelerate because there's a force of attraction between two masses. Big masses like the sun or earth can really extend gravitational force for long ways. Electric force is actually the electricity that is the electrons, the negative charged particles around the atoms in our finger. And if we come close to another object, like to push a wagon, it's our electric force of the electrons in our finger getting close to the electric charges in the wagon that actually provides that push. And almost all the forces we studied in that unit when we were doing that first unit were coming from the electric force. These last two are stranger. You don't see them that often, but the strong nuclear force is what holds an atom together. The protons really have not like to be together. They're both positive, and they're very close together in the nucleus, and so a strong force has to bind those together. As a matter of fact, once you get just far enough on the larger atoms, for instance, like uranium or some of those radioactive ones, it's just big enough that strong force no longer can hold them all together, and that's what causes them to radioactively break apart, to split. Whereas the nuclear weak force governs how it holds some of the smaller particles within the nucleus itself, and it governs when a little atom can be given off in order to make the nucleus more stable. If it's a little particle of electron or an alpha particle, those kinds of things are going to be governed by the weak force. So there are four forces that are out there, and the electric force we're going to examine in more detail. Electric repulsion, we've just said here, is this one. That's the one that we've been studying really when we talk about tensions or force of push. Now, how did they gather electricity to study this? Early on, these are the late 1700s, mid 1700s, so some of the founding fathers of the country were involved, Benjamin Franklin in particular, but there were others that were going on. A lot of that was in Europe, but like I said, Benjamin Franklin was in touch and was a statesman and then getting some of these ideas, but it was by friction. There are going to be three ways we talk about it. Rubbing or scuffling your feet on something gives friction, gives you a charge. We're going to talk about induction or pushing electrons by scaring them from a big charge somewhere else. The last one's going to be through conduction, by touching and allowing electrons to pass. The first one is that they realized quickly that if you, like you said, walk across the carpet, you can build up a charge, and then if you touch the knob, it will discharge and you'll feel a shock. As they looked at many, many different things that would touch each other and sort of leave electrons, they realized some things like our human skin or fur or hair, that's the material that's on the top here, is not very good at holding its electrons and is willing to let them fall off onto another object. So if you take a balloon and rub it in your hair, your electrons are lost from your hair into the balloon. If you get into the middle here, these are more like clothes or cotton or wood particles, and they're mostly neutral and don't hold a great charge. They sort of hold their electrons well, but they don't steal them from others. So you'll notice they don't give you the same sort of static, although they can give you some, depending on how dry that area is, as much as others. So these materials right around paper are neither good at losing nor good at taking. So they end up not gathering a lot of static electricity. Once you get down into amber and wax materials, they start to gain static on them pretty well. Rubber balloons and other kinds of rubber, hard rubber on like a baton or something along those lines. Here's an example of rubber material, and it's not soft or flexible like your shoes. That's just soft rubber. Okay, all the way down until you get to a lot of these plastics. PVC is a great example. If you ever cut a PVC pipe and all that dust really clings to the outside of the PVC tube, all the way down to ebonite, which is the best at stealing electrons and grabbing electrons on it. So that was what they would do. They would charge materials up, or they would take a sphere or something and touch it with some kind of fur. The electrons would be pulled, and they would pull them up into a lot of places, not just stealing them and being able to build charge up, but to store it someplace. And that's where I want to switch from how do they get it by just contact, or like you say, shuffling your feet on carpeting. But where do they store it? And a lot of times what they would do is they would store it into something like a Leyden jar. A Leyden jar is just a jar with tinfoil on the inside and tinfoil on the outside. If you could pull the electrons from the outside and push them on the inside, for instance, by induction or by scaring the electrons in the outside, by building up charge or something like that to scare the electrons to go inside, and then you disconnect the outside from the inside, you could hold a lot of charge. This is what we came up with as the modern tool called a capacitor. Capacitor is a hidden way to store a ton of charge in case you need it in a hurry. A lot of times people put it in their speakers so that they can really push the base, push a lot of electricity if needed, and then it'll go back into storage. But it's only there for a short section to get some more pop in there. But the thing with the Leyden jar is you could store up to a farad, which we'll learn tomorrow, that it's a lot of electricity. And even Benjamin Franklin, who was studying induction, found out on occasion when he would accidentally touch the inside and the outside together that he pretty much tased himself one time until a point where others would be unconscious. And some of the stories are interesting. A far less sort of violent sort of version of that is just taking a balloon. If I charge this balloon with the electrons from my hair, this will have a charge on it. Typically, I can put it up against the wall, and then this is going to show where the electrons, the extra electrons in the balloon, cause the molecules to have sometimes plus-minus sides to them, and they'll turn the negative side inward, leaving the plus there. And so then there's a natural attraction. If you've put a temporary charge by scaring the electrons away, this should stick to the wall. Okay, it's very humid in Texas, so that isn't going to work, and that's why I've directed you to some YouTubes to see some of those examples of static electricity. Just couldn't get it after several days of trying on film. But you'll see some examples online. Now, that charge then could be used to run, other kinds of things, or how human tissue or how animal tissue would respond to it. We started learning that our muscles run by electricity. One last way I'll just mention real quick is induction. Is you can take a balloon, and if you have two spheres that are metal and they're touching each other, you could actually put this balloon close, which would scare the electrons away, and then when you separate the two, one's got a plus charge, one's got a minus charge. And finally, you could charge up something like that balloon and actually physically touch a metal conductor, and those electrons would then cover the surface. They would just work their way across the surface, and that happens pretty quickly. But those are different ways we can capture electrons and be able to store them for studying, how much charge, how much repulsion, and those kinds of things that were going on, which is a lot of what was going on in those late 1700s. So let's get you a chance to play with some of these problems to see if you get which ones get the electrons, which ones give them up, becoming charged.